All right, question number 5 says to find the centroid of the tetrahedron E bounded by the plane x plus y plus z is equal to A, where A is a positive value, and the coordinate planes. Appeal to symmetry where appropriate. Okay, so I've drawn a picture of our solid up here. So we have this plane x plus y plus z is equal to A, and given that A is a positive value, our intercepts of this plane would just be at A, okay? And so then we have this four-faced pyramid shape, right? That's this tetrahedron for the solid, and our job is to find the centroid. All right, so first thing we can say is just really by the shape of our solid, we can see that if we're going to find the centroid, which is assuming uniform density, then the coordinates of our center of mass, our centroid, will have to be the same. In other words, we're going to lie along this diagonal that consists of all points where the x, y, and z coordinates are equal. Okay, and since our figure there is nice and symmetric with regards to that diagonal, we can see that that geometric center point, the centroid, would lie along that diagonal. Okay, so this is nice because it's going to allow us to cut out now two integrals we'll have to compute. We just cut it down to one. Okay, so now let's go ahead and compute the mass. And for the mass, we're just going to integrate our density function, which is constant, over this solid E. And as far as setting up the bounds of integration, well, I've gone ahead and let z vary first. So first think about letting x and y be fixed, and we'll let z vary from 0 when we're in the xy plane up to the height on this plane, x plus y plus z is equal to a. And there, just solving for z, we see that that height would be a minus x minus y. So for the triple integral, the bounds for z will be from 0 to a minus x minus y. And now as far as the region in which x and y can vary, well, if I project this solid onto the xy plane, I'm going to be covering this triangular region down in the xy plane. And the equation here of this blue line you see is just x plus y equals a. So just set z equal to 0 in the plane equation. And I'll go ahead and fill this region out with vertical strips. So y would vary next, and it'll vary from 0 on the x-axis up to the height on the blue line, which would be a minus x. So those are our bounds for y. And then finally, we're going to stack these vertical strips as we let x vary from 0 to a to fill out this region. So those would be the bounds for x. And I've gone ahead and just computed this integral. It's not terribly difficult, maybe a bit cumbersome, but you wind up getting k times a cubed over 6. All right, so now let's go ahead and compute, well, one of these moments. I really only need one by this symmetry consideration that we already have made. So I'll go ahead and compute the moment about the YZ plane. So in other words, I'll go ahead and compute x bar. I think pretty much all the integrals are on equal footing when it comes to difficulty, so there's not really an ideal choice there. But for this YZ moment, we're going to integrate x times our density function over our solid E. Notice the bounds of integration are the same, and now I'm integrating k times x. And I've gone ahead and done that computation. You wind up getting k times a to the fourth over 24. And so x bar is going to be that yz moment divided by the mass, which we computed up here. And now when you take this ratio, you get a divided by 4. Okay, and so then, since the coordinates are all going to be the same at our centroid, this will be the location of that centroid, a over 4, a over 4, a over 4, right? Quite a nice, pleasing result. Okay, we'll stop there. Thanks.